So this morning we're going to be discussing about coordination chemistry. So the coordination chemistry, which has to do with the complex compound, that is the complex ion compound, that one we're going to be discussing about this morning, and we're going to start with so we're going to start with module 1, unit 1. That's what we're going to start from. Okay, so when we're talking about coordination chemistry, the coordination chemistry uh, has to do with what we call the those compounds, that are related to complex ions. And when we're talking about compounds that are related to the complex ion, here in this place, we're actually talking about some compounds, under what we call chemical combinations, where we have what's called the ionic combinations, we have what's called the covalent combinations. So we learned that under what we call the covalent combinations, we have what's called the coordinate covalent combinations. So they are the one we're actually talking about in this place. So with respect to what we call the coordinate covalent combinations, there we have what we call these complex ions that we're actually talking about. Now, these mentioned complex ions that we have here, we have our majority of them are formed. I'll be giving you some structures of the complex ions, then we see exactly what we have in that. So take for example, where we have what we call the FeCN, we have Cn, we have Cn, 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 we also have Cn in this place. This particular compound we are seeing on the board, this is the compound of Fe into brackets, Cn close bracket 6, then we have this there. Now, the compound you're actually seeing in this place is a complex ion, as you can see, which are coordinate covalent compound, as you can see in this place. Now, let me quickly buttress this, that what you are seeing in this place is called the central atoms or the central ions. That is exactly the one that you are seeing, which is the what? The ion there. Now, apart from this, that we have many other related complex ions that I'll be mentioning in this place. For example, now we also have a compound like this, where we have Cu, okay? Then we have what we call the H2O. We have this, we have H2O. We also have H2O in this place. This compound that you are seeing in this place is also complex ion. Take note of that. So this is copper in the middle, which is the what? The central atom, the centrally placed atom there. They're being surrounded by what we call the H2O. Now this is copper 2 tetrahydrate. We also have what's called the copper 2 tetraamine, where we have Cu in the middle, we have NH2, we have NH2, we have this, we have NH2 as well. All this one that you are seeing in this place, this is copper 2 tetraamine. This is also a complex ion on its own. They are under what we call coordinate compound. Okay, so as you can see, this Cu in the middle here, we call it the ligand. Take note of that, the ligand that is actually present there. They're being surrounded by the rest of the what? The rest of the anions, as you can see. But in this case, we are actually dealing with what we call the Lewis, take note, Lewis acid and Lewis base. Okay, that is exactly what we're actually dealing with here, precisely speaking. So let us now dive into the concept of what we call the coordination chemistry in this place. Now, when we're talking about coordination chemistry, Coordination chemistry is the foundation of modern inorganic and bioinorganic chemistry, which contributed deeply into the development of chemical industry and medicine. Now, that is to tell that the backbone of the modern industries and medicine has to do with what we call the coordination chemistry in this place. And so, what does this coordination chemistry? What does it base on? Now, this is what we have to understand. The coordination chemistry actually based on the complex ions or the coordinative compound. Take note of that. That is exactly what it's based on. It deals with preparation, such as the work of the Warners, a Swiss chemist. It deals with what we call the preparation productions. That is the way of synthesizing many related compound, which has to do with the complex ion compound. Okay, now in this case right now, we shall now dive in deeply and discuss more concerning this particular unit that we have right now. So concerning what we have here, let's first of all define what's called the complex compounds. Complex compounds. Is it that you call them complex compound or you call them what you call coordinate compound? Okay. Now, what is the exact definition of this mention? Complex or coordinate compound are molecules that possesses a metal center that is bound to ligand, that is atoms, ions, or molecules that donates electrons to the metals. Now, in this place, if you look at the definition that we have there, we said complex compound or coordination compounds are molecules that possesses a metal center that is bound to ligand. Okay, now the ligand that we're talking about, we said they are atoms, ions, or molecules that donate electrons to the what? To the metals. Now, that is just the definition of what we call the complex compound. Now, those complex can be neutral. That's another point there. Those complex that we're talking about, they can be neutral to charge, okay? And at the same time, they can be charged. That's another point there. Now, when the complex is charged, it is stabilized by neighboring counter ion. Now, when a given complex compound is what? Is charged. Now, what does that mean? That means there must be neighboring. That means when you have a compound, okay, in which one of them is charged, okay, take for example now towards this particular one that we have here, NH2. Now, when one of them is charged, it is being countered so that it can be balanced, okay, by another one which is called a counter ion. Exactly. So if it is charged, it is being what? It is being counter ion balance. That's just the fact there. But it is not charged, then it is not counter ion balance. Okay. Now, but this is being usually done by what we call the neighboring counter ions. Okay. Now, they are formed by the reaction between the Lewis acid and Lewis base. Yes, this is exactly another point we have to discuss about here right now. So when we're talking about Lewis acid and Lewis base, okay, it should be noted that the Lewis acid, they are electron donor, while the Lewis base, they are electron acceptor. That's just another point in this place. The Lewis acid, they are electron donor, okay, while the Lewis acid, they are electron acceptor. Okay, so if they ask you, how are these complex compound formed? How are these complex compound formed? So the definition you can actually give them here is that they are formed from the reaction. They are formed from the reaction between Lewis acid and Lewis base. Sorry for the interruption now. So I'll be back in this place in a very short period of time. So now, as I was saying in this case, so I said the CU is the central place as one that we have there. Then we now have the rest, surrounding it. But the problem assigned to this right now is that you see that majority of them, they have exceeded the number of the CU that is available. The same thing happened in the case of what we call the AG, where we have AG, NH2, we also have what we call NH2. Normally, if you look at the nature of silver only has what's it called? Silver only has just one charge, okay, and now is carrying the molecules of amine, which is NH2 alongside itself. So here we go. They normally exceed the one that is available. That's just the fact that they normally exceed the one that is available. Okay. Now, then we have to talk about this carefully. So let's talk about the coordination complex. Then we talk about what we call the central atoms or ions. We talk about the anions. We talk about the numbers of the coordinates that they have and the valence that they have on them. Here we go. Now, concerning base, this is where we now deal with most of the complex ions that we have available. Then we tend to look at what are those things that they possess. Okay, what is their nature? How do they look like? How do you recognize them? Okay, so I am starting with this one here in this place. Now, right now, I'll be mentioning few of them in this place right now, so that we can actually understand what we are doing in this place. Okay. Now, for the few of them that I'll be mentioning here, then we shall be looking into the first one that I have here, which is Ni, where we have CO, close the brackets, we have 4. Then, now, in this place, this is where we have what we call the nickel, and we have what we call the what's called the CO in this case. And if you check what we have here, we have 4 of it. Now, from here, the central atom in this place will be what? Will be nickel, Ni. So, if you look at nickel is coming from where? It's coming from what's called the transition metals. That is it. So, mostly, it's transition metals that's involved in this, what's called the formation of complex ions that we're talking about. mostly transition metals. Okay, so the central atom is what is the Ni there, then followed by what we call the CO, which is the anion or the molecules that's involved. Then we now have what we call the number of coordinates. The number of coordinates from here is just 4, as you can see in this place. That's it. The number of coordinates that we have here is what is 4 in number. Now, the valence of the metal that we have in this place is just 0. Now, that is to tell you that this one here is neutral. The nickel in this place is neutral. It does not have any charge. Now, the next one that I have here, I have Fe, Cn close bracket 6. Then we have 3 minus in this case. Now, if you look at what we have in this place, this is iron, okay, and we have the cyano in this place, okay. So where we have what's called the hexacyanoferrate, okay, this is a hexacyanoferrate compound. Now, in this case, we have what we call Fe3 plus. The central atom there is Fe3 plus. Where does it come from? Iron itself, which is iron can be Fe2 plus, iron can be Fe3 plus. You know, they have variable oxidation state. These are one of the characteristics. This is one of the characteristics of what we call the coordinate compound. Okay. Now, then the anion that we have there is the Cn, which carry charge, which is minus in this case. And when it comes to the complex, number of coordinates that we have there, we have 6. Where is the 6 coming from? This 6 that we have in this place, that represents the number of the coordinates. So the Cn, which is the cyano, is the what? Is the coordinate that we have there. And the charge of the metal is what? Is +3. Then another one that we also have there, we have what we call the Ag NH3 close bracket 2. And here we have plus. Now, definitely the central atom here will be what? Will be silver, which is Ag, then which is plus, then followed by NH3 in that case, which is the anion, and then we have 2 coordinates. Look at it here. The coordinates in this place is what? Is 2. And so for the Ag, it is +1 there. Then another one that we also have there is where we have cobalt, Co into bracket NH3 close bracket 4. Then we have Cl2. Then eventually we have plus in this place. Okay. Now, with respect to what we have here, this is cobalt, this is NH3. Now we have 4 here, we have 2 in this place. So the numbers of coordinates that we have here, they are 6 in number. How are they 6? We have the primary, we have the secondary. This one here is 4. This is 4 in this place. This one is 2 in this place. So 4 plus 2 will give you what? 6. That means the number of coordinates there is what? 6. But the central atom here is what? Is the cobalt itself. That is the central atom, which is what? Which is 3 plus. Okay. Now, from what we have there, the anion there are 2 in number. What are the anion? The NH3 and what? And the Cl. Exactly. They are the anion that we have in this place. Now, what else you have there? The valence. The valence of the metal is what? Is +3. Or you write 3 plus. Now, that is another point there. Then, that we also have this is right now is another point we also have in this place right now is the last one that I have here, which is the Cu H2O, which is 6 in number, and there we have something like this, 2 plus. Then we have the following there. The Cu is the central atom, and it is 2 plus. The anion that we have there, this is or the molecule H2O. So the number of coordinates there is 6, and that one is +2, precisely speaking. So all these ones that we are actually seeing in this place, there are some of the coordinates complex that we have, their sum of the coordinate complex that we have, and also the important information concerning them. Now, let us now move to what we call the one has contributions to coordination chemistry. Who is the one has? One has is a Swiss chemist, okay, who also won Nobel Prize on his work on what we call the coordinate compound or complex ions, precisely speaking. So what one has worked at length, to give a valid information, preparation, properties, physical properties, chemical properties of a related coordinate compound. That's another point I want you to note there. Now, in this case now, here we go. How does the monas, go about his experiment? How does it arrive in the course of his experiment? Okay, so this is how monas work on it. Monas is one of the dedicated chemists, precisely speaking. So it happens that it works on the reaction between what's called the AgNO3 together with what we call the chlorides. So in the process, it tries to mix them together, mixing AgNO3 together in the presence of ammonia, and also using what we call the chloride alongside. So in the course of this experiment, at the end of the day, it was able to arrive at several conclusions, concluding that, okay, there is formation of precipitate and there's a formation of unprecipitate in the experiment. After further was got reacting most of this chemical related compound together, was able to arrive in the course of his experiment. So that is how owners contributed. He produced as many as possible what's called complex ions. Yes, he produced as many as possible. He gave property about them. He gave IPAC nomenclature on them. You can see that this contribution is extensive contribution. So at the end of the day, while there is formation of what we call the AgNO3 and also formation of AgCl, where there is precipitate and one without precipitate, then what are the conclusions from Warner's experiment? So they can ask you to mention maybe 4 conclusions of Warner's experiment. Now, this includes number 1. So number 1 point there is that Warner's, on his conclusion, that is on his experiment, number 1, central metals atoms contain primary and secondary valences. That is it. Central metal atoms contains what we call primary and secondary valences. That is conclusion number 1 there. So then number 2 is that primary valence is ionizable. It is the oxidation state of the central metal. So when we say ionizable, what does it mean? It can be discharged. And because it can be discharged, it is the what? It is the primary state of the central metal. Number 3 is that secondary valence is not ionizable. When we say secondary valence is not ionizable, what does that mean? It simply means it cannot be discharged. And because it cannot be discharged, that will give rise to what we call coordination number. So there is differences between what we call the oxidation state and what's it called? Coordination number. Okay, so coordination number is quite different from what we call oxidation states. When we say coordinate number now, take for example, where we have Fe, Cn, close the bracket 6, then where we have this one here, even if it is just plus that is in this place, for example now, the coordinate number in this place is 6. Coordinate number there is 6. Now, the numbers of, what's it called there? The valence of metal there is what? It's just plus. Even if it is ordinary form like this, let's say it is an intellectual question. Okay, so that is exactly what we're talking about here. Now, that is that one there. Number 3, secondary, okay. Number 4 rather, the spatial arrangement of the anions and molecules satisfying secondary valence will tell the shape of the complex. Now, what does that mean? When it comes to spatial arrangement, the arrangements that we give to what we call the anions, okay, will determine the shape. Take for example now, where we have what we call a related compound of this type. related compound of this type, Ni followed by CO, close the bracket, 4 in this place. Now, this compound that you are seeing in this place, this is what's called the CO here, which has coordinate number of what? Of 4. Because of the 4 here, the 4 that you have in this place will determine the shape. That is Ni followed by, we can have CO here, CO, CO, and CO. That is it. Now, what do we call this one that we have on the board? We call it square planar. As you can see, is it not a square shape? Yes, it is a square shape. Square planar. Planar in the sense that this is diagonal, this is diagonal. That is it. Square planar. You know. Now, we have as many as possible numbers of them like that. So let us try and look into complex ions and also primary valence, secondary valence, and possible shape. So I'll be exposing about their valences in this place right now. So let me begin with this one here, the complex, where we have the primary valence, secondary valence, and possible shape. So this is where a question can come out in form of, filling the gap. So when the question come out in form of filling the gap, please, it is not necessarily the one they have in their material. Okay, they can bring the question from any angle. There are as many as possible. Let me just use the word hundreds of complex ions that have been discovered so far. Okay, they are also part of chemistry as well. So in that case, so they can go and bring question from anywhere. So we'll be looking into how to calculate the numbers of primary valence, secondary valence, and possible shape that they might have. So starting with a compound of this type, here we go, which is 4 here. The primary valence is 0. Why is the primary valence 0? Primary valence is 0 because in this case, you realize that there is no any charge attached to it. Yes. So, and mostly this is the one we're actually referring to there. So no charge that is attached to it. The Ni is the primary valence, no charge attached to it, as you can see. So, but for the secondary valence that we have there, the own number there is 4. That is it. And for that, they will be taking what we call square planar as their own shape. That is the shape that they will be taking, the square planar. The second that I have there is what we call the K4, followed by Fe, Fe. Now, here we go. We have primary valence, we have secondary valence here. For what we have in this place, Fe, which is the primary valence here, is +2. Then secondary valence, which is Cn, 6. Okay, so this one here is 6. And lastly, what is that shape? The shape of this one here is called octahedral. So why is that shape octahedral? This is the reason. From the word octa means what? Octa means 8. We have K there. K, everything connected to K4 is just 1. Okay? That is, the numbers of atoms of this one is what? Is how many there is 4. So everything connected to K is 1. Everything connected to Fe is just 1. 1 plus 1 to give you 2. So 2 plus 6 in this place to give you what? 8. That means the Fe, okay, will be surrounded by the what? By the K4 together with what? With Cn. That is it. Now, the next one that we have there, we have what's called Ag, where we have NH3, 2, then we now have Cl in this case. Now, Ag in this place, which is the primary valence, is just what? +1. Ag is +1. Now, for the secondary valence that we have here, how many are they? Two. Two are present there. Now, what will be their shape? If you count everything that you have in this place together, you realize that this one here is 1, this one here is 2. Okay, now we have another one here that is outside. We shall be talking about this later. This one here is present outside. Now, the normal structure is AG, where you have NH3, we have what? NH3. Then you can add the Cl to anywhere you want to. Since it is going to be linear, you can add it from this axis, Cl, and so to counter it and ensure that everything there is what? Is balanced. So this type of shape that we have in this place, this type of structure rather, we call it what? Linear. Linear is exactly what we have there. And lastly, what do we have in this place? We have what we call the Cu. The Cu, which the primary valence is 2, that is the compound of Cu into brackets H2O close the bracket 6, in which the primary valence of the Cu is +2 and the secondary valence is 6, and they also have what we call the octahedron. They have octahedron. That is their own shape there. Now, we have two categories of what we call this of this related compound. What are their categories? We have the category of what's called the electrolyte and non-electrolyte complex. These are the two categories of a given complex ion. We have electrolyte and we have what's called non-electrolyte. So let us dive into this deeply. In a very simplified manner, the electrolytes, they form precipitates. While the non-electrolytes, they form unprecipitate. They are unprecipitate. That's it. In a very simplified manner, the electrolytes are the complex ions which precipitate and only satisfy the primary valence. They satisfy the primary valence, while what we call the non-electrolytes, okay, they form unprecipitate and they are meant to satisfy the what? The secondary valence. That is all there. So now, in the case of primary and secondary valence, based on what we have here, okay, we have different compounds, that stand in the position of what we call the primary valence and those that stand in the position of what we call the secondary valence. Non-electrolytes, this is a complex ions which form unprecipitate, satisfied both primary and secondary valences, which is the what? Coordination sphere. So they are meant to satisfy the what? The primary and secondary valences. Okay, now, and they eventually form what we call the coordination sphere. Now, but when it comes to electrolytes, are complex with the net negative charge. Yes, these are the complex with what? The net negative charge, which cations or anion can balance out charge. So in this case, they have what we call the counter ions that balance them up alongside. So we're given some typical example in this place. There we have the compound of Fe into brackets. We have Cn close bracket 6. Then we have 4 minus in this case. Okay. Now from what we have here, these 4 minus that we are seeing in this place now, if we can balance it with K4, what will happen? There will be formation of K4 into brackets Fe, Cn, close bracket 6. That's what we are going to have there at the end. So in this place, what we are talking about, the electrolyte and non-electrolyte. Now I believe you get the point we are talking about here. So I repeat, non-electrolyte, this is a what? A complex ions which form unprecipitates, satisfied both primary and secondary valences, which is the what? The coordination sphere. But when it comes to electrolytes, the electrolytes, okay, are complexes with negative charge, okay, which cations, that is this one here in this place, They are electrolytes, as you can see, because they have charge. So they are being there is what we call counter ion, and so they are being counterbalanced by what? By negative or positive. So this one that you are seeing here now, K4 in this place, is a what? Is a positive charge, which is meant to counterbalance the what? The negative charge that is present in this place. You can see that the ion is not there. So this one here, we call them electrolytes. This one here, we call them what? Non-electrolytes. That is it. That is it. Because there's no any charge in this place anymore. Okay? Now, the non-electrolytes are complex with zero net charge. As you can see, do we have any charge in this place? No. There's no charge there at all. So because there is no charge there at all, then we call them what? We call them non-electrolytes. So now, let's talk about this carefully. Let's mention few of what we call the electrolytes and non-electrolytes. Among those that I have here with me, I have the cobalt, which is the CO NH3 6. The cobalt related compound in this place, CO into bracket NH3 6, close the bracket, we have Cl3. Now, this compound that you're actually seeing in this place, okay, the precipitates, the molecules of the chloride in this place, which has to do with the chlorine ion, they form what we call the precipitate in this place. Now, it's just what? 3. That is the mole of the Cl, chloride ion precipitate. Look at it here, Cl3. It is 3 here. Now, what class does this one belong to? It belongs to the class of what's called the electrolytes. Now, the ratio of electrolytes in them is just 1:3. How do I mean by 1:3? This is it. From what you have here right now, cobalt is just what? Cobalt is just 1 here. And chloride is what? Is how many here? Is 3. So that gives rise to 1:3. As simple as that's there. Now, the next one that we also have in this place, we have what we call the trans, CO, NH3, close bracket 4, followed by Cl. Then in this case, we have closed the major bracket, we have what's called Cl. Of course, this one, they are green in color. Now, in this place, when it comes to mole, okay, mole of chloride ion precipitate, the mole of chloride ion precipitate in this place is how many? Is 1. The one that we are seeing outside there is just 1 there. Nature, they are electrolytes. That is their own class. And what is the ratio of the electrolytes? The ratio is 1:1. Look at this one now. 1:1. 1:1. So we have 1:1 for this. And the last one I have to discuss about it right now is the CO, where we have NH3, close the bracket, Cl3. Cl3. Now, you cannot compare the compound A to this particular compound A. These two compounds is quite different from this. Why are they different? This is it. This one have the cation outside, Cl3, Cl. Does this one have anything outside? No. So for that reason, the ratio here is just what? It's just 0. Nothing there. What is their nature? They are non-electrolytes. That's it. So the two that I mentioned here, they are electrolytes, while this one in this place is what? Non-electrolytes. That is exactly what we have there. Let us talk about the ligand. Yes, the ligand. Now, when we're talking about ligand, this is what I want you to know there concerning ligand. Ligand are Lewis base, which coordinates to central metals. Take note, ligand are Lewis base, which coordinate to what? To central metals, atoms or ion in a complex. Now, this is when you have Fe, you now have Cn, 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 Cn. 1, 2, 3, 4, 5, F6. These are the ligands that we're talking about there. This one, Lewis base. They are the ligand that we're talking about there. Lewis base are those bases that are ready to accept electrons. Okay, Lewis acid are those acids that are ready to lose what? Electrons. Simple. Okay, now with respect to that, here we go. Now, when we're talking about ligands, I've said it earlier that they are what? They are Lewis base, which coordinate to central metals, atoms or ions in a what? In a complex. It can be heteroatom. What are the heteroatom? Such as we have H2O, NH3, we have P, that's Phe. Take note of that. This Phe, phosphine. So this one that we have here, they are heteroatoms. The heteroatoms, and they're also what we call ligands. Okay. Now, having lone pairs, those that have lone pairs, when we say lone pairs, I believe you know what I mean by that. Usually have what we call negative charge there. So that means ligands can have lone pairs, negative charge, such as Cn minus, SCN minus. We also have what's called Cl minus. We have what's called Fe minus. All these ones that you are seeing in this place, okay, there are those that are negatively charged, okay, and they have what's called lone pairs. Lone pairs. And the last set that I have in this place are unsaturated hydrocarbons. When I say unsaturated hydrocarbon, then you can come across compound of what's it called? Ethane is present there. It can be aromatic, such as benzene. It can be macromolecules like protein, vitamin, and porphyrin. All these ones that I've mentioned in this place, they are typically ligand. So now you know what ligand is all about. Why Fe in this place is the central atom there. Don't forget the what's called the chlorophyll 2, that it contains, is found in chloroplast, and because it's found in chloroplast, just recall that, okay, or what is actually being used, magnesium is being used as what we call the central atom there. They're being surrounded by the rest of the related compound, which enable what's called the green plants to attract ultraviolet, thereby manufacturing their own food. So we have what we call monodentate ligands. So we are going to start with the different types of ligands in this place. Anywhere you hear the word mono, you should believe or know that it is what? One. So a ligand with one donor site. A ligand with one donor site. That is what we call the monodentate. So one donor site, that means they only have rooms for one donor. So here we go. We have such as for monodentate, we have such as what we call the H2O, we have NH3, we have Cn minus, we have Cl minus. All these ones, they have one donor site. We have bidentates. Bidentates, they have two what? They have two donor sites. Example of those that have two donor sites, we have what we call the ethylene amine. Ethylene amine. Exactly. They have two donor sites. Okay. Now, apart from ethylene amine, we also have what's called the oxalates in this place. Take note of that. So another one that we also have there, we have tridentates. Yes, tridentate ligand. They have three donor sites. Take note of that. They have three donor sites. So for the tridentates that have three donor sites, those that have three donor sites, which are called the tridentates in this place. One of the typical examples is diethylene triamine. Diethylene triamine. And the next one that we have there, we have what we call the quadridentate. From the word quadri, they have four donor sites. Okay, so because they have four donor sites, they also combine together in in their various forms. And typical example here is what we call triethylene tetraamine. Triethylene tetraamine. Triethylene, take note, triethylene tetraamine. We now have what we call the polydentates. Those of polydentates, they have many donor sites. They have many donor sites. Polydentates, they have many donor sites. And typical example in this place, including what we call the EDTA. A student of chemistry, you are conversant with this EDTA because it has been used in various fields. And what is the full meaning of EDTA? That is ethylene diamine tetraacetate. That's it. Ethylene diamine tetraacetate. That is the name of the compound. Now, we have those that we call ambidentate ligand. They have two heteroatoms, and any can be used to coordinate with metal depending on the reaction condition. So, because they have two heteroatoms, they can bind together, and it depends on the nature of the chemical reaction that will determine where they are to followed. Now, what are the applications of this mentioned organic related complexes compound? Sorry, inorganic related complexes compound. Now, number one is inorganic analysis. It is employed in quantitative and qualitative analysis to detect presence of metals. Now, when we say presence of metals, remember the case of what we call the compound of the compound present in what we call add water. Yes. What are those things that are present there? You see magnesium chloride, magnesium sulfate, see compound of calcium chloride and calcium sulfate present there, or calcium hydrogen triiosocarbonate, they are present there. All those ones, if you want to detect them, you can easily make use of this mentioned here. Number two, purification of metals. Yes, majority of them are used in purification of metals such as gold and nickel, can be purified using complex compound. Now, number three is what we call the industry. In most of this industry, they also utilize what we call these complex ions, okay? In petrochemical industry, nickel, platinum, and rhodium complexes are used as catalysts in hydrogenation reaction. So when we say hydrogenation reaction, what is hydrogenation reaction here now? Okay, conversion of what's called alkene to aldehyde. So in this case, such as cobalt and rhodium complexes are used in hydroformylation. Yes, hydroformylation. Number four, medicine. Yes, it has wide application in chemistry, such as in curing of cancer. Okay, use of EDTA as anti-poisoning agent for lead poisoning. So if there is presence of lead poisoning in someone, we can use what's called EDTA as anti-poisoning agent to quickly detect and cure it. Then another one is what we call the cisplatin to cure cancer. Also, still under the medicine, technical, okay, complexes in imaging of internal organ in living organism. They use it to do the imaging of internal organ. We also have oranophine. Yes, the oranophine gold complex for treatment of what we call arthritis is being used there. And another one is what we call the budotytane. Yes, budotytane. Budotytane is used as what's called the anti-cancer drugs. So all this one they were obtained from what we call the complex ions. Now let's talk about this important biological complexes. That's number 5. Photosynthesis, I made mention of something related to this earlier, where there is magnesium as the central atom there. Remember what's called the hemoglobin, the one that carries oxygen from one place to another in the body system, utilizes what we call the ion, okay, as the central atom. Don't forget the one that helps to store oxygen within the body system, which is the myoglobin. Also make use of what we call the central atoms, which is what the iron there. All these that I've mentioned are the various 5 applications of what we call the coordinate compound or the complex ions, precisely speaking. So on our next class, we are going to be discussing, the next part of this topic, which has to do with what we call naming of a related compound. Thank you.